Certainly welcome to work with your neighbor.
He's over the other side. You have to keep going like inside. I don't think they're exactly. I know that like
This part I'm not.
And so if it's the inverse, I'm multiplying the right side.
Do you think
So it'd be
multiplied both
side?
on the outside of that.
yeah. So this actually is
Yeah, no, this is good.
Basically, like that's it. It's like we just sure. We didn't really talk about it.
what would be a good first move? There's a few things we could do here, but what could be a good first move?
Multiply both sides by inverse of A.
Inverse of A. Does it matter where I multiply?
Yes, on the front.
Can I do that?
No.
I actually can't. That's not the same necessarily. I mean, I can, but I have my agency. Mathematically, I won't get the right. So if I'm going to multiply A inverse on this side to cancel out with this A, then I need to do a left multiplication over here with it. It should have started with like, what would be the if these were just numbers and we were solving for X, what would be the thing you would naturally do?
Cancel out A and B.
What?
Cancel out A and B.
Oh, if you had A inverse and A, yeah, you can commute some things and cancel out, right? Yeah, another thing you might do is just start dividing by things on this side. Right? But there's no division of a matrix. Okay, whenever you think about, oh, I need to divide by this matrix, then you want to be thinking about multiplying by an inverse. So that's what we're doing here. Multiplying by this inverse, and then A times A inverse. A inverse times A is going to be the identity. And we'll have dx A inverse, E inverse. That's A inverse I plus A. Okay, what's the identity matrix times another matrix? For the identity matrix, I think we mentioned before. It's the matrix with ones down the diagonal. It's the square matrix, so n by n matrix that has ones down the diagonal, zeros everywhere else. Because if you take this matrix and multiply it by any matrix where the multiplication works, you'll just reproduce that. You'll just reproduce that next matrix. So X is our multiplicative identity. So this I times this B will just be B. So okay, what's another step I could do? Oh, here, let's simplify this side. Over there. So I can distribute out. So the marker on the floor. I can distribute this out. I have to be careful though, because if I'm multiplying this on the left, when I distribute out, I need to keep that A inverse on the left hand side. So Actually, it doesn't matter in this case because you would have read about an inverse in the original matrix. Those do always commute. The identity matrix does always commute. So in this particular case, it actually doesn't matter. But in general, it does. So this becomes A inverse, and A inverse times A becomes. All right, then what do we do? What do we do next?
Side by B.
We multiply B inverse on this side. Inverse, inverse there. So distribute that out to get XA inverse B inverse, and then B inverse. I can distribute that out to get B inverse A inverse plus B inverse, and then what can I do from there?
Go back a little bit. Based on the how you went from A inverse I to A inverse A to A inverse plus I.
Oh, you bet. So right here. Yeah. So this I is the identity matrix. So the identity matrix multiplied by any matrix will just reproduce that. It's like multiplying by 1 with 2. So it's the multiplicative identity. And then A inverse and A, by definition of the inverse. When I multiply those, I get the identity.
Okay. Yeah, okay, I was like, what is I? I thought I was just like another matrix. I didn't
Oh.
know what it meant, like, 'cause I knew,
Okay. Yes, we do use I to represent the identity matrix. I think exclusively. Okay. Good question. Any other questions? Okay. What's something else I can do from here?
By B on the right hand side.
Multiply by B on the right hand side. And we could save ourselves a step. I'm not going to just multiply by B, I'm going to multiply also by A. On this side, and then I multiply B here and A here. And then this B inverse times B will become the identity. Then the A inverse times A will become the identity. So I just end up with X. X times Y times Y. Which is X. Well, unless you're doing Roman numerals, then that's true. But, yes.
Formed by B. In that order of.
Good question. So that question was, does it matter that I wrote BA? What could I have written AB? Yes, it matters. One of the big things, I've got a slide on this. One of the big things that we need to emphasize with matrix multiplication is two matrices AB multiplied together is not necessarily the same as B times A. They don't hold the commutative property. Some special matrices will, or some special occasions they might be the same, but in general those aren't the same. So when I do multiply over here, I want to be sure that I do B times A, so then I get the B times the B inverse together. To get that I go. And the A times the A makes A inverse will end up together, and I'll get the A. Good question. And then over on this side, that down. It's just X times the identities, however many identities, it's just going to be X. On this side, I'm going to distribute that BA. And I need to keep it multiplying on the right. So B inverse A inverse BA plus B inverse BA. And this B inverse B will become the identity matrix. So we can write that as B inverse A inverse BA plus A. Did I do that right? Other questions on this? A few key things. If I multiply on the left, I need on this side of the equation, I need to multiply the left on this side of the equation. Okay, to maintain things. You multiply on the right on this side, and you multiply on the right on this side. You'll be tempted, but don't commute the multiplication. We can commute addition, and that's fine, but not multiplication. I have some boring slides on that. Then we'll come back to 2. So here's a fairly practical problem, and very similar problems are found in almost every field, social science and earth science. Okay. In this particular example, the context is trying to estimate someone's body fat. It's kind of a pain to actually calculate. You take your weight, you also weigh yourself in water, and then you do some calculations, which isn't always easy to do. So the research that was happening here was they took a bunch of other measurements. They have the height and weight, they have the age, and then they have, most of these are just things you do with the tape measure. They're just centimeters around your wrist, centimeters around the ankle, centimeters around the hip, centimeters around the chest. So things you could easily do at home to calculate, to estimate your body fat percentage. So the question is, this, like, we want this as the outcome. And there are a lot more cases. In this study, there were about 250, and these were all male. So we have this as the outcome, and we want to reproduce this column if possible with this information. Okay? The question is, how do you go about doing that? So think about that for a little, and then tell your idea to your neighbor. Doesn't have to be related to this class. There's stuff you could do related to what we're learning, but it doesn't have to be related to this class. You might have other ideas.
Won't you get? Say you just didn't know about that. How do you know everything? We hope for a perfect one, but like, how do you do that? Like, start everything else. How do you?
That's like a
You're right, though. Basically, you're trying to measure the variance and body fat based on the variance and everything else, all at the same time.
All right. Okay, anyone have an idea they want to share? Yes.
Put all the information into an augmented matrix with the body fat being the augment, and then try to get it into reduced row.
Nice. Okay, this is very close to the peanut butter fat problem, right? We kind of have a goal we want to reach, and each of these is like, sorry, it's not peanut butter fat, protein and fat as an outcome, and we have certain foods like peanut butter and bread. We're trying to figure out how many servings of each of these do we need to get this. So thinking like, hey, let's augment the matrix. And so we can take all of these things, put body fat over here on this other side, augment it, and then start row reducing. Great. That will work under a few certain conditions. When would that work?
Well, the moment you have more cases than you have columns, that's something where you're gonna have to hope that your cases line up real well. Otherwise, you have situations where you have factors equaling, like, no, maybe 0 of everything is equal to something, or those kind of weird inconsistencies.
Yeah. So one way to state that is that as long as this column, the body fat column, is in the span of all of these, then we can do that strategy. Okay. What happens if it's not? That's the other question. But someone else had an idea about what we could do to solve this.
Said what I was gonna say.
You did? Okay. Yeah, this is nice. So that's a perfectly viable thing to do as long as this is in the span of these other things. I did hear someone say we're trying to figure out the constants of each of the columns. Oh, here, let me come back. So this idea, this problem, this fundamental problem of trying to predict with information that you have, is a fundamental problem in lots of science and social science that I've already mentioned. You guys have heard what it's called. It's called regression or multiple regression. When we have lots of these variables and not just one, it's called multiple regression. And it's related to all of these things and more that we've talked about so far. Span, linear independence, dot products, orthogonality, linear combinations, solving systems of equations, matrix multiplications, transpose, inverse of a matrix, rank. We could list a few more. And this is actually the first problem where so far it seems like a lot of the stuff that we've talked about, we already had other ways to do and other ways to talk about. But this problem actually shows the power of understanding these to be able to actually calculate the model rule. So this y or y bar, show that's a vector. I should have put bars on all those. We can think about them as columns. So A1, A2, A3, A4. I heard someone say we're trying to figure out what constants we multiply by each of these so that we can add them up and get y. And that's one way to think about what we're doing. We're trying to find a linear combination. What's the linear combination of these columns that we would then equal y bar, that outcome. So you could write it this way: x1 times a1, x2 times a2, x3 times a3. Trying to figure that out. Or if you're in a stats class, they'd write it out as like a times age plus b times weight, c times height. I don't know what velocity is, but you can they'd use the names instead of following them. So here we're trying to figure out that linear combination of all of those columns, like how to weight each of those or the length of each of those to get to y. If we can't get y exactly, that's when we're going to use some of the other ideas that we have, and we'll attack it at the end of class. So we can modify what we're going to do. Okay, so here's a few boring slides. These are right from the book. Just to emphasize a few things. Some of these seem pretty natural and straightforward. And I would encourage you, if you're not convinced that they're true, write down a couple simple matrices for A and B or A, B, and C, and actually do the calculations to convince yourself that it doesn't matter if I add A plus B or B plus A.
Yeah, I had a question. The zero matrix looked like an O. Is that like a symbol that they use, kind of like I?
Yep. So yeah, this is the zero matrix. Yeah, nice. This is the zero matrix. It's like I, and it just represents the matrix that's the right size to be the same size as A. If we add those together, we get nice. Other questions? Yes.
Would F mean something different if it was A times C plus D? Like
Would
the
A means something different if it was what?
Would it mean something different if A was in front of the C plus D?
So if it was A times parentheses C plus D.
Yeah.
No, it turns out that because of where does this go? Let's be on the other one. Scalars commute. So it doesn't matter if I write C times A or A times the scalar C. That doesn't matter. A scalar multiple just multiplies every single entry of the matrix by that number, by that real number. So it doesn't matter which way I write it. That a scalar times a matrix does commute. So it doesn't matter, since this is just C plus D is just a scalar. I could write it on either side. It wouldn't change. So good question. Okay. Other questions with any of these? These are easy to state, but what you need to do is, like, these are just symbols. You have to bring the understanding, right? You have to bring the literacy to and the meaning to what these mean to make sense of them. A times B times C, it's associative, so I can choose which order to do those. I can just multiply the first two first or the second two first. They're the same. And again, to convince yourself, you could write down three matrices, 3 2x2 matrices, 1 2 3 4, 5 6 7 8, -1 -2 -3 -4, something like that. And then actually do the calculations to convince yourself. Notice left distributivity. That's distributivity. If A is on the left side here, when I distribute it in, it needs to stay on the left side. We use that in solving. Same thing with the right here. This constant, the scalar times a matrix product. I can do the scalar product first with a matrix and then multiply it. It doesn't matter. Okay, this K also commutes. So as I mentioned before, move that around. And the multiplicative identity, this identity, it moves, although you might have to change the size. That's what the M and the N are. Here for the identity matrix to make sure that you can actually do the multiplication. But the identity matrix does. And what's key here is what's not on the list. AB does not equal BA. Commutativity doesn't. One way to convince yourself of this, we did do a little bit with how a matrix is a transformation, and each of these could represent a transformation, like the plane, for example. If you do two transformations, the same transformations in different order, you don't end up in the same spot. So, for example, you can rotate 45 degrees and then reflect along the x-axis, or I can reflect along the x-axis and move 45 degrees. I'm not going to end up in the same spot.
Does it matter when you're doing exponents, which side? So like say you have a cubed, does it matter if it's a times a squared or a squared times a?
It doesn't.
Okay.
So good question. Is there another hand?
On that though, of course, I mean, just like everything else, but you do everything inside the parentheses. So a times b squared is like supposed to be a times b first and then square the whole thing.
Oh, so a times b quantity squared. A times b quantity squared.
Yes.
Yeah, that's a times, yeah, that's ab times ab. But so since it's associative, you could, if you wanted to, multiply the BA in the middle first if you wanted to, and then multiply that by over. But you can't.
You can't do a squared times b squared.
Okay.
Right. So it's not the, yeah, it's not a squared.
And if it was without parentheses, a times b squared, would it matter if you did a times b or a times b squared?
So this, if you have this,
Yes.
right, then it does not matter. That's a times b, and it is associative. So I could do this, or I could do these two first. Nice. Others? There's always commute with matrices. We already talked about that. If you start on the left, it stays left, or starts right, it stays right on the distributive property. Then your matrix always. Okay, properties of the transpose. This first one, why would A transpose? Get you back to A. It's pretty easy to convince yourself, right? Can you do this? Well, I flipped it and I rewrote it, or I reflected it and rewrote it, and then just do the transpose again, and you end up back. So that makes sense. Here you can also convince this that if you add A and B and then transpose, well, you could transpose those first, A and B, and then each entry that you add up together, they're going to end up the same place if you do this. So again, these are nice ones. Try all these once with just some or a couple random matrices. Convince yourself that they're true. The transpose of a constant is just a constant. You can think of it as a 1-by-1 matrix if you want. Transpose a 1-by-1 matrix, you just have that same 1-by-1 matrix. This is the one that's a little bit crazy. So initially you'd think something to do with powers, and you'd think, oh, that's A transpose, B transpose, and that's not the same. Okay, this is not the case. I have some slides on this to explain why. But again, you could just write out some 2-by-2 matrices, do it in this order, do it in that order, and you convince yourself. And there's a power one there. Okay. So this is one way you could prove this transpose property, that A times B, that quantity transpose is the same as B transpose times A. This is an example of a proof you could do. This is just for the 2x2 case, where I pick each of these to be an arbitrary value. I use the 1, 1 and the 1, 2 and the 2, 2 to represent the positions. So this is little a is in matrix big A, 2, 2 is the second row, second column, is the second row, first column. And so AB transpose, I can rewrite as this. And then I can do with that actual multiplication. So I have A11 times B11 plus B12 times B21. So that's where this term comes from. And A11, B12, A12, B22. That's where this comes from. So we do that multiplication, and then I transpose that whole thing. And so now this term that was up here is now down here. See 1, 1, 1, 2, 1, 2, 2, 2, 1, 1, 1, 2, 1, 2, 1, 2. Okay, so that's here. These diagonals stay the same. Now the hard part is factoring it down and seeing that I could rewrite this as this this B matrix transpose and this matrix transpose. So B11 A11, B21 A12. I get that right there. This term is B11 A11. Sorry, B1 it's not that. B11 A21 plus B21 B22. Where'd that go? B22. No, but that should be. Mistake. I wrote these down. I have a slide here that's easy to see. So this is 1, 2, 3, 4, and A, B, C, D. Then you can see that A times 1, 2 plus C, or 2C, that's here. 3A, 4C, that's there. 1B, 2D, that's there. 3D, 3B, 4D, that's right there. And this is B. This was the matrix B, and it's the transpose. This is the matrix A. So you can follow with that. This one's easier for me to see the. Okay. The matrices don't have to be the same size. They just have to be compatible with multiplication. So a couple things to talk to your neighbor about here. So I have an A, I have a B. What size will AB transpose B? And then what if we thought AB transpose equaled A transpose B transpose? What size will A transpose B transpose be? Enough B's in there for you. So think about those two questions in bold and talk to your neighbor about it.
It's not like my weird way of thinking about it. There's like 3 across. One falls on its side.
So if you've already grabbed yours, go ahead and. Just so everyone's aware, we're passing the homework back one more time because I know that there are people who are here who haven't grabbed their homework yet, so.
Please pull it out so you doesn't have to haul your homework all over campus. All right. What about this first one? What size will A, B transpose be? So raise your hand, let me know. Okay. How many rows will there be? Show your fingers. How many rows will there be? Okay. 2. How many columns will there be? 3. Okay, so yeah, if I do the A times the B, this is doable. I'm going to end up with a 3×2, but then I transpose that, I end up with a 2×3. How about this second case? What if I tried A transpose, B transpose? People shaking their head. It doesn't even exist, right? I can't even do that multiplication. So this is one way to help convince you this can't be true. So, but the B transpose and the A transpose, if we do B transpose times A transpose, we're okay. Just a note on proofs. We haven't been required to do a lot of proofs. There's no proofs coming up in this first exam, but we're going to be using proofs more to help understand matrices and properties of matrices. I know some of you are very hesitant about trying to write proofs. We'll help you out a bit. This isn't a proof-based class, but we're still going to, when they cut it down to 2 credits, they cut out a lot of the proofs, but we'll still use them as a way to help understand what's going on. You might be asked to do some on your homework, maybe some straightforward
With
ones.
that,
On,
can I actually make some comments because I've started to notice this
Sure.
with the homework. So an example is not a proof. And I'm starting to mark off if you just give an example of when it's true, because that's not a proof, because it can be true in one case and not true in another case. And then the other thing is, if it specifies the size of a matrix, go ahead and use that then. But if it doesn't specify size, you need to do a general case. You can't just do it in a 2×2 matrix to prove that it's true. So just 2 small things.
so this is an example of a way to do a general size matrix, is you can write out the entries this way. And then you can keep your dots in there as you work through this. So, thank you for that. A lot of the first proofs that we do in proving basic properties, we end up going down to this level. But once we've proven a few things, we use the properties we've proved to prove more powerful things. And if you can keep from going down to this level, try to do it. It saves you a lot of work, and it helps you to practice using the properties and better understand what's going on. Excuse me. So this is an example where you don't have to go all the way back down to this level. It might even be hard to do so. So the theorem is if A is invertible, then the inverse of A is unique. So one way to prove this is, let's suppose there are 2 inverses, 2 different inverses. Or just take 2 inverses of A. We'll call them B and C. And we're going to show that B actually equals C. So any 2 inverses you get there actually. So I can start with B. I can rewrite B as B times the inverse. I can rewrite that inverse as A times C, because C is an inverse of A. And then I can use the associative property to write it as B times A. The B is an inverse of A. And then we get the identity, and the identity times C is just C, so C equals B. So any 2 inverses that we pick for A actually have to be equal, so there's only one. Yes?
There's more than one inverse matrix, right?
So this is a proof that there's only one inverse matrix.
So then you assumed that there were 2, and then you proved that they were the same.
Yeah, that's right. Any ones that we pick end up being the exact same one. So it has to be one. Nice. Yes.
So you said that we have to keep doing the proofs on our homework, proofs on the exams.
Any proofs that we have on the exams, we'll give you some warning to think about those things you should be able to prove. Okay. Let's try to be fair. Okay, so we're back to this problem. So our last task is to do number 2. Before we dive into 2 turns out to be exactly what you need to solve for the regression problem, for that prediction problem that we were doing with body graph. So I'm going to do the simple case. Suppose we only had 2 prediction variables, A1 and A2. Then if Y, our outcome variable, if that was in this plane, that was the span of A1 and A2, then we could do just what you guys suggested, which is augment the matrix and just solve. row reduce and solve, and that'll tell us how much of A1 and then how much of A2. But if it's not, then we can use some other tools that we've been developing. So this is what I'm trying to predict. If I can't get it exactly, I want to get as close as possible. What's the closest I can get to the end of Y? To the head of Y? The closest, I can only get to places that are in the span of A1 and A2. I'm taking linear combinations, which create, in this case, a plane. In our other case, it'll be some like what 14-dimensional hyperplane. Okay, so I can only get into here. What's the closest place I can get?
Is it a projection?
It is a projection. This will be perpendicular right here. Any place I move from here will be further away from that head. So it's a projection problem. So, and this AX, this is a way to represent a combination of A1 and A2 with X's in the vector being how much of X, like X1 times A1 plus X2 times A2. I've represented it as A times X. The matrix A as its columns are A1 and A2. So I could make, in this case, you could think of it as a 2x2 matrix, and X here would be a 2x1 matrix, and I'm trying to figure out the values of X so that I can get to this point that's closest to Y. But now I can use the geometry. I'm dealing with two vectors here that need to be orthogonal. What do I know about orthogonal vectors? The dot product is 0. So I know that AX, that optimal AX, when I dot product that, do the dot product with this vector, which is Y minus that AX, then that has to be 0. So now I used the tools, the powerful tools that we've developed to create this equation, and now I have to solve this equation. And now that we're doing some matrix algebra, we can start to solve this. X here is X is a vector. So Y is a vector, A is a matrix. So take 3 minutes and see if you can, how far you can get here. I already gave you that hint of start by rewriting this as a transpose, multiply AX. Even if you can't get all the way, you should be able to make some progress. It does matter which one you transpose. Because this is not the 0 matrix, this is just the number 0. So if I'm not careful, I don't want this. I don't want this. I want this. Because this one gets me 1 3, 1 4, 2 3s, 2 4s. This gets me 1 3 plus 2 4, which is 11. So this is the same as the dot product. 1 2 3 4. So I want to transpose this first one to get that. So I could rewrite that as this transpose. And that's the same as the dot product. You're transposing this first one. Yes.
Are scalars equivalent to 1x1 vectors or 1x1 matrices?
Sort of. Not really, because a 1x1 you can't multiply by a 2x2. Right. So this isn't defined as a matrix multiplication, but it is defined as a scalar multiplication. So sometimes sometimes it's good to think about them as 1x1s, but other times it's not so good to think about them. All right. See what we can do on this one.
Where's the last one? Can't work. That's how that works.
Blind.
The negative transpose.
Transposed rival AX, which you can do besides.
Why would one transpose?
Because AX is equal to 0. Transposing. Change the
Okay. So there's a few different paths you can take to try to figure out a solution to this. So one thinking is, even off the bat, if I multiply these two things together and there's 0, what do I know? Either one of those. Maybe one way to do this is that each of these has to be 0. So I could take this and set it equal to 0, and I could find a solution. And I could take this and set it equal to 0 and find a solution. This one is if x bar equals 0. This is one that you get. This is the solution that you get if y is actually in the span of the columns of A. You might not see that. I'm not expecting you to see that right off the bat, but this is equivalent to transpose. If I transpose both sides, I just get y bar equals ax, and this is like an ax equals b. I can just multiply by a inverse on both sides.
So since you were talking about like how since 0 is just a constant right here. So if you're multiplying a matrix by a vector, you're going to get a vector. So how can you set that equal?
So this is a dot product. We started with a dot product. Dot product is you end up with a scalar.
Yeah.
So when we do this, it will be one number, a 1-by-1 matrix, actually a 1-by-1 matrix, but it's only it's a real
Yeah,
number.
but just like it, like then if you try and separate the two out, you say, oh well, a matrix A times the vector x, like that can't equal.
Right. Yeah. So I should have those. This should be.
So Kate, like can you just decide to make it a vector then?
Well, we have to understand that, hey, this actually is a vector. This actually is a vector. So when I set that up, I would signify that, oh, I'm thinking that this is going to end up with a vector, so I have a vector, a 0 vector. It's something you have to bring to the equation. So we get these, but that's actually not, none of these are the solutions that are going to help us.
I was just gonna ask, so for the left, do you need to transpose it to do that algebra? Like you transpose it and then you transpose it back at the end.
This one?
So the solution on the left, so we started by doing the transpose at the very beginning. You're going to be doing the method on the left. You do it with-
Yeah, right. I could have started that.
Okay, gotcha.
Okay, so we're running out of time here. Here, there's two different things I could do. One thing I could do is I recognize there's an x bar and an x bar here. So I have something times x bar and something times x bar. If those are equal, what's an assumption I might make?
Those coefficients are equal.
That these somethings have to be equal. So one thing I could do is set those equal to each other and then solve. And if I do that, I get x
Looks like he just started.
Redistributed.
X bar transpose A equals Y bar transpose A. And what can I do here? I want to get X by itself, right? That's what I'm trying to find. That the values in this X are going to tell me how much of each of the columns I weight. That's going to be my coefficient of each of my columns. So I'd like to get rid of this. How am I going to do that? Yeah, I'm actually going to just write it this way. I'm going to multiply by A transpose A inverse on this side, and A transpose A inverse on this side. And so I get X bar transpose equals Y bar transpose A transpose A inverse. And if wanted, I could take the transpose of both sides, so I just have X bar. This turns out to be a really, really important equation. This is called the normal equations, and gives you a very straightforward way of finding the optimal, those optimal coefficients for your model. Okay? This is what your calculator does when you run regressions. It just runs this guy right here. Yes.
Is that how transpose change?
Oh. Yeah. When we get further into the inverse matrix, we'll see that an AB inverse
He's just pretending.
is B inverse A inverse. So it switches the order. All right, so everyone, have a good day.
Yeah.
Right there. Line 4. Then you can take this one. Then he's able to transpose A by multiplying steps first.
So you just transpose stuff where you want.
Apparently.
But like, why didn't he transpose A?
Because they're orthogonal. Transpose it.